So now we're going to look at a problem related to some data that is normally distributed and look at a type of problem that we might be asked to solve. We're going to look at the pop bottles and those machines and the data we gathered for those. Okay, given above is all the information that we calculated before, the fact that the mean and standard deviation for machine 1 were 12 and 1.41, and the mean and standard deviation for machine 2 were 12 and 0.14. Our first question is related to machine 1. What percent of pop bottles will be filled less than 10.59 ounces on machine 1? Okay, now we are told that the volume for these two machines is going to be normally distributed. What that tells us then is that these percentages that we talked about before for the normal curve stay intact. Okay? What we're going to do though is we're going to label the x-axis specifically for this data set of machine 1. That means that here where the mean would be x bar, we're going to actually put the mean of 12. Now as you know, as we move to the right, it said x bar plus s. That means to take the mean and add on a standard deviation. So we take on the mean and we add on a standard deviation. That means that this point will be 13.41. So we'll have 34% of the data between 12 and 13.41 ounces. Now, because it's normally distributed, we know that we pick up another 13.5% of the data as we come out to x bar plus 2 standard deviations. But we're going to put in specific numbers. We're going to take our mean and we're going to add the standard deviation on twice now. So that means that we get 14.82. Okay? Picking up an additional 2.35%, we come out a third standard deviation. So we're going to add on 1.41 again. That puts us at 16.23. So we can generate these values along the x-axis by adding on the standard deviation once, twice, 3 times. Now remember, this is a symmetrical curve, so as we move to the left of the mean, we see the same distribution of the data, meaning coming back 1 standard deviation, we pick up 34% of the data. Coming back 2 standard deviations, we'll get another 13.5% of the data. Now how do we figure out the x value? Well, we take the mean of 12 and we subtract off the standard deviation not once but twice. In other words, from that 10.59, let's take off the standard deviation again. So the value along our x-axis is going to be 9.18. Okay, to get that last 2.35% of the data, we come back another standard deviation, so a total of 3 standard deviations from the mean. So if we just subtract 1.41 again, that gives us this value. Okay, now what we can do is answer our question. Our question is, what percent of pop bottles will be filled less than 10.59 ounces? Well, we can locate our data value of 10.59, there it is. And since we want the percent that is less than that, we will just grab these percentages, 2.35 as well as 13.5 gives us a total of 15.85. So we're talking about approximately 16% of the data will be less than that. Now think of the significance of that. Maybe 10.59 was significant to the company because they realized that anything below 10.5 ounces is going to start to be noticeable to the customers. So based on the fact that this is normally distributed data, they could locate that data value and then figure out what percent of the time these pop bottles are going to be noticeable to the customers. Now they know about 16% of the time their customers are going to be dissatisfied. With this information, then the company can make an informed decision as to whether to recalibrate the machine, or perhaps they're just going to leave it just depending on the price to do that. They may look at that 16% and say that's not much, or if it's a small company, 16% of their customers being dissatisfied could be a very substantial amount. So this is just one example of a type of problem we can solve if we know that the data is normally distributed. We're going to look at another example. This time we'll look at machine 2, and then we'll also look at one involving SAT scores.